Okay guys, so now that we have a couple of videos on Sterling numbers and Bell numbers in our channel, I think it's time to move on to Catalan numbers now. And in this video, I'm gonna give a short and sweet introduction to Catalan numbers. On this screen, you can see the recursive formula for Catalan numbers, also the exclusive formula, 1 by n plus 1 and then 2n choose n. And also, there are a few ways Catalan numbers are used, right? So, like either to find these arrangements or in binary tree or decoupage. Yeah. Okay. So, let me first give you a definition of Catalan numbers that I personally like because there can be any definition, right? I mean, there are a lot of definitions, but like the one that I like and that will be helpful for us, let me give you that. Okay. Catalan numbers, CN. Definition would be define Cn to be the number of ways to correctly arrange n pairs of opening and closing brackets such that every opening bracket this opening bracket has a matching closing bracket right, and a no closing bracket ever appears before its matching opening one, right? So I guess the definition is clear. Let me show you a few examples, right? So let's say if you want to find CF1, then like you just have one pair of brackets, and then like the only way to write it is like this, right? So CF1 is this one. Okay, so let's say now for CF2, you can either you have like two pairs of brackets, right? You can either write them like this, right? Or you can have like this. Yeah. So there are two ways, but note that you cannot write it like first of all this one and this one and this one and this one. Like, I mean, that doesn't make sense, right? Like two closing without opening bracket doesn't make sense. So first of all, there should be opening bracket for it to be closed. And yeah, these are the two ways. So CF2 is equals to 2, right? Similarly, let's say if you want to find CF3, you can maybe have something like uh this, right? Or maybe you can have something like uh this, or maybe something like this, or maybe even something like this, or maybe even something like, I'm not sure what to make. Wait. Okay, so I can have I can have something like this thing, right? And then I have this thing, and then this thing and this thing, right? So when even over here, like this also satisfies the condition, right? Every opening bracket has a closing bracket and no closing bracket ever if forced before it's matching opening bracket, right? Okay, so I think these are all the ways. So C3 is 5. So this is how you can actually compute the Catalan numbers explicitly, right? But in this video, not just this, like because we have to find, like, let's say C4, C5, or all these other numbers, then you need some formula, right? To get that formula, you first actually need this recurrence relation, and after you have the recurrence relation, you can actually find the formula from recurrence relation. So let's see how we can actually find the recurrence relation. So let's say you have found up to C sub n. Okay, now like you have actually found how much it is. Now let's say if you want to find C sub n plus 1, Now I'll also how can you use recurrence. Okay, so in C sub infinite C sub n plus 1, right? So okay, so let's say you have, okay, all the like this possible arrangements or pairs will be in this form, right? A bracket, like opening closing bracket, and there again some arrangement inside that and some arrangement outside that, right? So like maybe there can be just one pair of brackets over here and then remaining n pairs over here. Sorry, because there's already one pair of bracket over here, so if there's one pair over here, there can be n minus 1 pairs of brackets over here, right? Pair of brackets over here, right? Because then like one pair of bracket and mentioned pair of bracket becomes n pair, and there's already one over here, and that becomes n plus 1 pair in total, right? So let's say if A has like two pairs of bracket over here, like in some arrangement, here can be n minus 2 pairs of brackets arrangement, right? So like all the possible ways, like if here's like n pairs of brackets being arranged, and there here it will just be like 0 pairs of brackets being arranged, right? So if yeah, so basically like uh in this fashion, if we just try to like sum up all these possible ways brackets can be arranged, so that will basically give us cn plus 1, right? So we are basically trying to use induction using the arrangements from the with the lower subscript. Yeah, to get cn plus 1. So let's see how the formula will be, right? So to get c sub n plus 1. Okay, so over here, let's say we want to arrange zero brackets over inside it. Like there's just this one bracket, this outer one, and then there's no such thing in A, and everything is over here. So the total ways for that will be C0 into Cn, right? And again, you can have, let's say, one pair of bracket in A, and then like all the rest of them in B, right? So that will be C1 into Cn minus 1, right? Similarly, you will just add up to Cn into C sub 0, right? Like n pairs over here and 0 pairs over here. So adding all these up will basically give you all the ways you can arrange n plus 1 bracket pairs, right? So yeah, so this is actually the recurrence relation, because we are using the like lower Catalan values to find Catalan at n plus 1, right? So we actually got a recurrence relation. It wasn't too hard. So this is just sum from k equals to 0 to n of ck cf n minus k. And that was exactly the recurrence relation, right? So using this, now you can find all the values. Like, okay, so till now we found c1, c2, c3. You can also actually find c0. If you don't have any pair of brackets, you cannot you just don't have any ways to arrange it. Like, and that's also one way. So we just define it to be 1, right? And then yeah, so now based on this values you can find all the values. Yeah, so let's say if you know c0 is equals to 0, this is actually enough to define Catalan number. This is also a definition, definition using recurrence, because now you can find c1 using a c0 times c0, right? Which is just 1 into 1, which is 1. Now c2 will be uh, c0 c1 plus c1 c0, right? And that will be 1 into 1 plus 1 into 1, which is 2, right? And that was it, right? It was 2. Now for c3, it will be c0 c2 plus c1 c1 plus c2 c0, right? And this is 2 plus 1 plus 2, which is 5. So that was what we got, right? Yeah. Again, for C4, it will be C0, C3 plus C1, C2 plus C2, C1 plus C3, C0. Now C3, C0 is 5, C1, C2 is 2 plus C2, C1 is 2 plus C3, C4 is 5. F5, 5, 10, and for 14. So this is how actually you can now find all the Catalan values, right? But again, like instead of you just like doing this using this recurrence and finding all those values using the like you forming up all the lower values, it will be much nicer if you have like explicit formula, right? And definitely there is, it's already on the screen. So let's try to see how we can find that explicit formula. So what we're gonna do is we are gonna use this recurrence relation, and also we are gonna use the tools of generating function. So let us first define this c of x, which is basically the generating function of the Catalan number, right? To be summed from n equals to 0 to infinity of cn x to the power n, right? So what we're gonna do is we're gonna use the recurrence relation of the Catalan number and make some manipulations to actually find a real polynomial. Like actual polynomial in terms of x and these things, which we again gonna break in infinite sum and actually compare the coefficients, which is again gonna we okay. So we're gonna find a polynomial which we are again gonna break into infinite sum, and then we will find some expression like over here, some expression for like for every n x to the power n, and then compare that expression and get c of n. So that's what our idea will be. Yeah. Okay. So let's proceed ahead. So now I'm gonna do something. I'm gonna make some manipulations like this. Okay. So what I'm gonna do is I'm gonna try to find this product c of x times c of x, and there's reason for it. And this will be sum from n equals to 0 to infinity c of n. And let me write it as like from a equals to 0 to infinity of c of a x to the power a, and sum from b equals to 0 to infinity of c sub b x to the power b, right? So this is c of x square. Yeah. I can write it as going from a equals to 0 to infinity, going from b equals to 0 to infinity of c sub a, c sub b x to the power a plus b, right? Okay, now what's happening is like a is also going from 0 to infinity, right? And b is also going from 0 to infinity, right? So, so because I want to write this as just a single number, what I can do is if I make a variable change, let's say n is equals to a plus b, right? And then this k is equals to this b over here. Yeah, if I make that variable change, okay, now let's see while a and b go in this range, how will n and k go, right? So what we can do is actually we can just let n go from 0, 1, 2, 3, and so on, right? And because n is sum of a plus b, right? So for n equals to 0, like b will just be 0. B can just be 0, right? Because in that case, like for n equals to 0, and because both of them are positive, b can just be 0, right? And in that case, a will also just be 0. Now in this case, b can either be 0 or b can either be 1, right? And in like correspond in the corresponding way, a will be 1 and a equals to 0, right? And while this is true, b can be 0, b can be 1, or b can be 2. And for each of these values, it will also take three different values, right? 2, 1, and 0. So the thing is, if you make this variable sense, what will happen is to get all these scenarios where a going from 0 to infinity, b going from 0 to infinity. Now we can actually let n go from 0 to infinity, and let b or let k go from 0 to just n, right? Because b is a positive number over here, and then this can just be like we saw that it can be like going from 0 to n, right? Over here it can be b0, b1, b2, b3, and corresponding to each case we will have a3, a2, a1, and a0, right? So that actually like covers all the previous cases. So this is actually a valid variable sense. So now using this variable sense, we can actually write the c of x whole square as n going from 0 to infinity and k going from 0 to n of now a will be n minus k and b will be k, and then x to the power n, right? Okay, now here's how we use the recursive relation of the Catalan number. Now the sum from k equals to 0 to n of c of k, c of n minus k, this is exactly just c of x. Sorry, this is exactly our c of n plus 1, right? This is exactly our c sub n plus 1, right? Because that was just what we did earlier, next to the or n, right? We are good till now? Yeah. So now what I can do is, because there is this c sub n plus 1, if I write 1 back over here, this will also become c of n plus 1 x to the power n plus 1, right? Now this sum is actually the same as the sum from n equals to 1 to infinity of cn x to the power n, right? Because there's just n plus 1, n plus 1, so instead of going from 0, you can go from 1 and write just n, right? Now that sum is again the same as sum going from n equals to 0 to infinity of c sub n x to the power n minus, like, the term we added over here was c sub 0 x to the power 0, right? And now we know that this is again just the original generating function for Catalan number, right? And we define that to be c of x. So okay, I forgot this square over here. I'm sorry, guys. Okay, so now our c of x square will be 1 by x, and this is again c of x. And we already know that c sub 0 is just 1, right? Yeah. Guys, damn. Why am I writing 0 over here? It's 1. That's why. I'm sorry, guys. This is 1, clearly 1. This is I'm doing a blunder. Okay, so minus 1 and x to the power 0 is also 1, right? So we have now this polynomial for c of x, and that's how we solve for the function c of x, and then again make it infinite series, and then from the infinite series we can actually find this expression in n, right? So that's what I was talking about. So we have beautifully used this recurrence relation of the Catalan number to actually get a polynomial expression for it. And this is, my friends, so powerful. I just cannot express how powerful this thing is. So x c of x square minus c of x plus 1 is equals to 0, and then now c of x becomes minus b plus minus square root of b square minus 4ac by 2a. Right, now there are these two expressions, but since our c of 0 over here, if we try to find c of 0, notice that all the terms will vanish except the first term where we have 0 to the power 0, that's 1, right? And here c sub 0 is the coefficient of 0 to the power 0, c sub 0 is 1, so this is the c sub 0, which is just 1. So c of 0 is actually 1, and we are going to use that thing over here. So we're going to use the fact that c of 0 has to be 1, right? Now if you take plus, this will just see, if you take plus, let's say if you take positive, you're gonna get c of 0 as 1 plus 1 by 2 into 0, right? And that just blows up. That doesn't really give us 1. But if you take negative, we will have c of x is equals to 1 minus square root of 1 minus 4x over 2x, right? And then if you try to find c of 0, right now it will again be 0 over 0, which is indeterminate, but you can take a limit, right? In the indeterminate, you can take limit. And if you use like L'Hopital rule, you will have c of x as, now that's 0 minus 1 by 2 root 1 minus 4x times minus 4 by 2, right? And yeah, limit x goes to 0, we're trying to find c of 0, right? So c of 0 is going to be, now limit x goes to 0. Okay, so now this is just 1 by square root of 1 minus 4x, right? This 2 times 2, 4 cancels with 4, and minus minus plus. And if you substitute x as 0 over here, this just becomes 1 by square root of 1 minus 0, which is just 1. So this actually works. So therefore, our c of x should be 1 minus square root of 1 minus 4x over 2x, right? So now we have like some expression rational function for c of x. Now the only thing we want to do is to write it as infinite series, so that we can compare the like coefficient of x to the power n and then get an expression for c sub n, right? So let's do that now. Okay, so first of all, for this one, let's go part by part. This one, the infinite series is just sum from n equals to 0 to infinity of, okay, the power is half, right? The power over here is half, and then choose n, and then minus 4x to the power n, right? This is just the binomial series formula. And now if I try to do some manipulations, I will have half minus 1 up to half minus n plus 1 by n factorial minus 4 to the power n x to the power n, right? And now that becomes sum from n equals to 0 to infinity, 1 minus 3 up to, this is minus 2n plus 3 by 2 to the power n factorial minus 1 to the power n, 4 to the power n, x to the power n. Now there are exactly n terms over here, and if you like just distribute the minus 1 to the power n to each of them, we will have minus 1 with 2n minus 3 double factorial, right? So that means kind of factorial, but each term is decreasing by 2. And then n factorial, 2 to the power n cancels to give 2 to the power n over here now, and x to the power n. So over here, now if you want to change it to like central binomial coefficient, what you can do is you can actually introduce uh, uh 1 by 2n minus 1 over here, right? So that this becomes 2n minus 1 double factorial. And again, if you introduce another n factorial over here, and 2 to the power n, this n factorial over here, then there will be n factorial 2 to the power n over here, right? X to the power n. But again, this thing is again just 2n double factorial, right? So now again, this product over here, now that product in the numerator is just 2n factorial, yeah? 2n minus 1, and then minus 1. This is now just 2n factorial by n factorial x to the power n, right? And now that becomes summed from n equals to 0 to infinity of 1 over 2n minus 1, and then minus 1. This is just 2n choose n x to the power n, right? Okay, so we have finally found a bit neater expression for 1 minus 4x, right? Now we actually had to find 1 minus the square root of 1 minus 4x by 2x. This was the original expression, right? So now if we give it a minus sign, the minus sign inside this sum will disappear, right? So that's something nice for us. Yeah. And now okay, so let me observe something to cancel this one. So notice that the first term in the series is actually just 1 by negative 1 1 1, right? And sum from n equals to 1 to infinity 1 by 2n minus 1. I'm just trying to separate the first term because that is just negative 1, and that's what helps us to cancel the 1. Okay, the fact that first term was just negative 1 is actually helpful, right? Because if this is just negative 1, now if I add 1 to both sides, the negative 1 is going to cancel out, and we have sum from n equals to 1 to infinity of 1 by 2n minus 1, or 2n choose n x to the power n, right? And now if I try to divide this by 2x, I will have, if I try to divide by 2x, so now I'm gonna have sum from n equals to 1 to infinity 1 by 2 2n minus 1, or 2n choose n x to the power n minus 1, right? And now I can actually let this go from, this is actually our entire expression, right? That we want to change. Now we are almost close. I can actually let it go from 0 to infinity, and I can have 2. Now this becomes 2n plus 1. This becomes 2n plus 2 to n plus 1, and this becomes x to the power n, right? Now I guess you guys know that I can write n choose k as n over k, n minus 1, k minus 1, right? So using this formula, what I can do is I can write this as sum from n equals to 0 to infinity 1 by 2 times 2n plus 1. I can actually take 2n plus 2 by n plus 1 outside, and the remaining thing will be 2n plus 1 by n x to the power n, right? Then notice that this 2 times n plus 1 cancels to n plus 2, right? So it seems like we are close, but again, we aren't really getting the same sort of expression that we wanted, right? Okay, so right now what we have in our hand is 1 by 2n plus 1, and then again 2n plus 1, and let me write it properly, 2n plus 1 and x to the power n, right? But over here, we are gonna get c sub n, right? And we know c sub n should be this thing, like 1 by n plus 1, 2n choose n. So it's not really same, but we again use this same formula. We're gonna cancel this 2n plus 1, right? And then, okay, so let's try to cancel that and see if we will be able to get it. Okay, we can cancel that, right? But over here, we will have n minus 1. And then we'll have 2n to the n minus 1. Again, that's not a good thing. I mean, that won't be helpful. So what we can actually do is, a better way would be to first, because we know that this binomial coefficients are have this property, right? I mean, sorry, yeah, this binomial coefficient, yeah. So we're gonna use that, and that will actually be helpful. You will see. So this expression can now be written as sum from n equals to 0 to infinity 1 by 2n plus 1. I can write this as 2n plus 1, choose n plus 1, right, using this property over here. And so now if I use this property again, I will have 1 minus square root of 1 minus 4x by 2x to be equals to sum from n equals to 0 to infinity of 1 by 2n plus 1, and then 2n plus 1 by n plus 1, and then 2n choose n x to the power n. Right now this cancels out. This is nicely sum from n equals to 0 to infinity 1 by n plus 1, 2n choose n x to the power n, right? I guess you guys also know that this is actually our this thing over here, this expression is also our c of x, right? So this is also our c of x, and our c of x was also this thing, right? Sum from n equals to 0 to infinity of c sub n x to the power n. Now from this equality, if you try to compare these two sums, we have sum from n equals to 0 to infinity c sub n x to the power n to be equals to sum from n equals to 0 to infinity 1 by n plus 1 to n choose n x to the power n, right? From here, we can conclude that the c sub n is 1 by n plus 1 to n choose n. And my friend, this is a powerful, beautifully derived formula. Because we used a lot of things to derive this. First of all, we actually had to derive the recurrence relation, and then from there, try to get this polynomial for c of x, and after getting the polynomial, use the binomial series, and again, over there, make some manipulations, double factorial, single factorial. Again, try to see how those terms cancel out, and then how again use some binomial properties, some property of combinations. That was a lot of things, guys, but the result here is totally worth it. Yeah. So now actually let's try to use that result to verify what we have been trying to find over here. So from this one, c sub n is equals to 1 by n plus 1, 2n choose n, c sub 0 is just 1, 0 to 0, that's 1, right? And c of 1 is 1 by 2, 2 choose 1 is 2 by 2, that's 1. c of 2 is 1 over 3, 6 choose, okay, wait. Get 4 choose 2, that's 6 over 3, which is 2, right? And c sub 3 is 1 over 4, that's 6, 3, which is 20 over 4, which is 5, right? Okay, yeah. So all these are actually verified. Let me find c5 as well. c4 is equals to 1 over 5, and 8 choose 4, and 1 over 5, 8, 7, 6, 5 by 4, 3, 2, 4 to the 8, 3 to the 6. So 5 have cancelled, 7 to the 14, yeah. So yeah, we get all the answers properly, and this works, right? So finally, we have defined Catalan numbers. We have obtained the recursive relation. We also proved the formula, and bang, we are now in a quite a good condition about this number. And then now I think we are good to go, and then also do some problems involving Catalan numbers in the upcoming videos. I hope you guys have enjoyed it, and I look forward to seeing you in the upcoming videos too.